Alright everyone, how's it going? This is going to be part 1 in a multi-part tutorial series on kernel extending Windows, and this is something that you've probably never seen a tutorial for before, considering there are like a dozen people in the world who do this. We're going to be starting with a fully stock, unmodified copy of Windows 7, and we're going to be defeating the PatchGuard security system. We're going to be implementing our own version spoof. We're going to be writing a lot of API functions. I'm going to kind of give you a basic primer on debugging applications and kind of figuring out why they crash, because there's a lot of applications that are either very poorly written or very hostile that do not work and that you'll have to add workarounds for a lot of times, things like that. And yeah, this is going to be a fun little series, so if you want to learn about, this kind of stuff, this sort of niche interest, then stick along. In today's video, I'm going to be starting by showing you how to defeat the PatchGuard security system, also known as kernel patch protection, which is just kind of the general sort of term for it in whatever OS, and PatchGuard is kind of Microsoft's sort of marketing term for it. PatchGuard was implemented in Vista. It's actually the successor to the Windows file protection from Windows 2000 and XP. And it's actually still one of the kind of main security features in Windows today in terms of like local security, sig checking the kernel and other things when they load and things like that, and it doesn't work very well. So I'm going to show you how to bypass it. For this, all we're going to need is IDA Pro, and we're going to take these three binaries from System32, ci.dll, winload.exe, and winload.efi. So ci.dll is the Windows Code Integrity module, and then winload is the Windows OS loader. And what we're going to do is we're going to put these into IDA, and I'm going to do a search for a sequence of bytes. And if we look at the nt status table here, we can see status invalid image hash. And this is actually the message that it prints out on the blue screen of death or whatever. Or typically in this stage of boot, it's kind of like a Windows preload type interface where it says Windows cannot verify the digital signature, blah blah blah. And this is the value. It's C0000428 in hex. So C0000428. And I'm going to sort this by instruction. So what we want to do is we want to actually change all of these move instructions. So we'll just start with this one, and we're going to have to do all of these. And we want to change this this int status value, C0000428, to just 0. And the reason we're doing that is because 0 in int status is success. So that will completely get rid of the bug check or crash there. Now, IDA does have an assembler built in, so you could try to do this, but it's not going to work for a lot of these instructions because, at least with this old version of IDA I have, the newer versions might work a little better, I don't know, but with this old one, it can't actually handle a lot of these more modern registers and stuff. So it's actually really easy just to do this by hand in machine code. So you can see here, it's in Little Endian. Endianness is kind of a interesting thing where some CPUs will read the sequence of, or the order of bytes in a multi-byte sequence. They'll read them in order, right? It's sort of referred to as like starting with the most significant bit. And then Little Endian, which is more common in modern CPUs, reads the byte order backwards. It starts with the least significant bit, and the reasoning for that is kind of technical, but more or less a lot of instructions will kind of just resolve out to a no operation in Little Endian. It's sort of strange CPU design stuff, but that's why. And so this byte order is actually backwards, so this is read as C0000428. But it's written 280400C0, and on x86 platforms, it's always Little Endian. It's always written like this. So I'm just going to change this to 0. 4 zeros, and as you can see there, that's changed. And pretty much, you just have to go through every single one of these. And actually missed this one, the top two. And you have to do that in all three of these binaries. So I'm going to go ahead and do that off camera because it takes a long time, and we'll come back when we're done. Alrighty everyone, so once you've went ahead and patched your binaries, I'm going to confess, these are actually ones I patched a couple years ago. They're exactly the same, but it takes a long time to do this, so I just went ahead and pulled these that I had saved. The next thing we're going to do is we're going to use the CFF Explorer, which is part of the Explorer suite. If you just search CFF Explorer online, you'll find it. And we're going to go to the rebuilder. We're going to uncheck rebuild PE header, and we're going to check update checksum. And we're going to save all of these. So let's go ahead and do that on all three. I'm going to have to actually open this one manually. Rebuilder, update checksum, save, and finally, rebuilder, update checksum, save. Okay. Now, we're going to run into a problem, which is that if we try to actually delete or rename any of these things, it's going to give us some issues. So we need to actually take ownership of System32 and give our user full permissions for it. To do that, we're going to take own /f. /f just means that we're specifying a file name, System32. And then we're going to iCackles. I don't know what this stands for. I'm going to be honest with you. I just call it iCackles, but it's a program for file permissions and stuff. These are built into Windows, by the way. System32/grant, and then you can just type your username here, or I prefer to use %username%, which is an environment variable in Windows that actually just contains your username, :f, and F means full control over everything. So that's going to give us full control over all of the files, and it's going to make us the owner of all of the files. Next, I prefer to actually back these up by renaming them instead of deleting them, just so that if I need to, I still have them. So we're going to do that. We're going to put our modified binaries in there. And then we're going to set the BCD settings. So we need to set BCD edit /set no integrity checks on. This makes it so that the actual bootloader in the MBR or the EFI doesn't sig check the OS loader, or else it'll fail. We're going to BCD edit /set recovery enabled off. This makes it so that Windows will not automatically go into recovery. You can still trigger this manually, but the problem is that when you have these modified binaries, it's going to say, oh no, those are corrupted. That's what it thinks, and it's going to try to replace them back. So this turns that off. And then this third BCD setting is optional, but I like to set test signing on, which disables the driver signature enforcement, so you can load your own unsigned drivers. And then we're going to go ahead and reboot here, and if the computer still boots up into Windows, then that means that you were successful, because otherwise, you're going to have a bad time. So let's go ahead and let it boot up here. And yeah, so that's how you defeat PatchGuard. Now, PatchGuard is only relevant, like I said, in Vista and up. If you're interested in old Windows NT or Windows 2000 or XP or whatever, then this is completely pointless, but at least maybe you learned a little something. So yeah. Thanks for watching, everyone. Let's go ahead and go into System32 here and show you that they're in there, that I didn't bamboozle you. There they are. So yeah. Thanks for watching, and I'm out. Goodbye.